So in this video, we will actually derive the time dilation effect directly from the Lorentz transformation. And so, as we did in some previous slides, previous videos, let's consider x and x prime coordinate systems here, and x prime system is going at velocity v relative to this x and y. This figure is not very nice, but these two x-axes are supposed to be parallel. So in that case, how can we figure out the time dilation effect? Let's see. In the time dilation effect, we're considering a moving clock which is at rest in this prime coordinate system. So delta x prime in that case is actually 0 by definition. So the equation that's convenient to use is the transformation equation that goes from the prime coordinate to the unprime coordinate system. So that's, for example, one equation for that is delta t equals gamma delta t prime plus v delta x prime. So in this equation we can put delta x prime equals 0, and then you get the time dilation effect right away, gamma delta t prime. So that's what we derived in the previous lecture using this light clock. But this shows that this time dilation effect is a general effect for any process. For any process that happens at a fixed point in this moving frame, corresponds to delta t prime in that coordinate system, which is shorter than delta t observed from a rest frame by a factor of 1 over gamma. So that summarizes the moving clock running slow, or in other words, time dilation effect as seen from this unprimed coordinate system. Let me mention a related effect, which is Lorentz contraction effect. Lorentz contraction. So using the same sort of argument, we can figure out the length measured from two different reference frames. So let's say that a rod is moving to the right here with velocity v, and this length of this rod is delta x prime when it's measured in this moving frame, which is in which the rod is at rest. So that delta x prime is basically the natural length, the true length of this rod, because it's measured in a frame in which the rod is at rest. So now we ask the question, what is the delta x? What is the length that we perceive when we measure it in this rest frame, which is at rest relative to that moving frame? So now one thing that you need to remember is that when we measure length in whatever frame, we must measure the left end of the rod and right end of the rod at the same time, because otherwise the length could be any arbitrary value depending on what time you measure the left end and what time you measure the right end. So that means in whatever reference frame you measure the length, delta t should be 0. Okay, so that means the Lorentz transformation equation that that is convenient to use in this case is the transformation that goes from x to x prime. And so let's say that means delta x prime in this case equals gamma delta x minus v delta t. And here as well as here we are using, well, here especially we are using the unit system where c is 1, as I often do. Now in this equation, what you can do is now put delta t equals 0, so that term disappears. So that means delta x prime equals gamma delta x. And remember, this delta x prime is the true length of the object measured in the rest frame of the object. So that means compared to that, delta x that we measure is actually smaller by the factor of 1 over gamma. And so so that's like saying a moving object looks smaller by a factor because delta x is 1 over gamma times delta x prime, and 1 over gamma for any velocity which is not 0. 1 over gamma is a number that's smaller than 1, and so that's the Lorentz contraction.